Hi everybody, welcome to day 14 of CPR. Today's episode is brought to you by the letter N, which stands for Index of Refraction, and that's something that is used to tell us how much light bends as it goes from one material into another. For example, the index of refraction for light as it goes from air into water is 1.3. Now, of course, what we really want to talk about today is the law of conservation of energy, and you can probably guess what that is all about, because you already know the law of conservation of mass. Whatever mass you start with, that's the mass you end with. You already know the law of conservation of momentum. Whatever momentum you start with, that's the momentum you end with. Law of conservation of energy, same thing. Whatever energy you start with, the amount of energy you end with is going to be exactly the same. It might change form along the way, but the amount is going to be exactly the same. So, law of conservation of energy, one way you'll often see it written is like this: energy is never created or destroyed, it only changes form. So to illustrate this, we'll do a couple of simple demonstrations. For starters, we'll just drop this book. Now I'm pretty sure our friend the spider gets pretty nervous every time I pick up this book. But when we drop the book, what's happening as far as energy is concerned? Okay. Well, if we say that the table is the zero potential energy, when I'm holding the book motionless up here, obviously it's got no kinetic energy. It's got nothing but gravitational potential energy, and the gravitational potential energy is at a maximum. And of course, as the book falls, well, the gravitational potential energy is getting smaller, the kinetic energy is getting bigger. In other words, the potential energy is changing to kinetic energy. So as it's falling, it's got various combinations of potential and kinetic energy. And of course, just before it hits, when it's an infinite distance off the ground, well, it's got no potential energy, it's got nothing but kinetic energy, it's going as fast as it's ever going to go, its kinetic energy is at a maximum. And of course, once it hits the ground, well, the kinetic energy doesn't just disappear, it's got to change into something, and what it changes into is heat and sound. There we go, maybe you can see that now. What it changes into is heat and sound. The sound is pretty obvious, the heat not so much, but imagine this. Imagine you're driving a nail into a board and there's a lot of impacts there, and if you've ever felt a nail after you've been hammering on it a little while, after all those impacts, that nail is getting pretty warm. That kinetic energy has been changed into heat energy. Same deal here. The kinetic energy, it impacts the table, and the kinetic energy goes to zero. It doesn't just disappear, it changes the heat energy. And of course you might say, well, what happens to the sound energy? Because you only hear the sound for a very short length of time. What happens to the sound energy after that? Again, it doesn't just disappear. It too changes into heat energy. Think about it. What is sound? It's a pressure wave moving through the air. And as it moves through the air and dissipates and gradually dies out, well, of course, it's making all the air molecules jiggle around, and that's what heat is, the motion of atoms and molecules. And of course, I didn't write it down here, but your maximum potential energy is going to equal your potential energy plus your kinetic energy, which is going to equal your maximum kinetic energy, which is going to equal your heat and sound, which is going to equal, well, ultimately all the heat at the end. All these different types of energy at various stages of the ball falling, they are all equal to each other. All right, suppose we take our poor spider here, who's apparently waiting like 8 knee replacements. He can't crawl around anymore. He depends on us giving him pushes. So if I give them a little push along the desk, what's going on with energy when that happens? Okay. Well, ultimately, I guess the energy started out as heat and light from the sun. Okay. And that heat and light from the sun, it was absorbed by some chickpeas. I ate the chickpeas last night. So now we've got chemical energy in my arm. That chemical energy in my arm, it gets changed to kinetic energy of the spider as it's moving, and friction changes that kinetic energy to heat. By and large, whatever energy you start with on Earth here, most of the time it ends up as heat. And then before we all boil over and melt and cook into nothingness, well, the heat gets radiated off into space. Yeah. Take a look at this right here. Again, if you trace back most changes of energy, the original energy source for most of them is going to be heat and light from the sun. And of course, the light, when it hits something, well, it gets changed to heat too. And ultimately, the final type of energy in any sequence of energy changes is going to be heat. And that, of course, gets radiated out into space, and we don't have to worry about it anymore. What we'll do next is we'll take a little more mathematical look at this. All right, here's an example. Let's talk about an Olympic ski jump, as in Olympic ski jumping, where people slide down a hill and then they take off for, I don't know, 80, 90, 100 meters is the amount they're airborne for. Now, of course, building one of these things is a huge engineering project. Like, you got to move a lot of earth, and it costs millions of dollars. And in the end, it's got to be safe for the athletes, right? You don't do those kinds of things by trial and error. You can't say, okay, go for it. Whoops, don't worry, the broken legs will heal in a couple months. For the next person, we'll make sure we expand our braking area or put our braking area at a slightly different elevation. Like, these things, they have to be engineered, they have to be calculated out beforehand. And this is what your typical ski jump looks like. I was lucky enough way back when, just after they built the Olympic ski jump in Calgary, I was lucky enough to tour around it. And actually, it wasn't a tour at all. You basically paid your money and you could walk all over this thing. And of course, here's the starting point, and it's a very steep drop down to the actual jump. And the actual jump is kind of interesting because from here to here, like if you're standing at the edge of the jump and you're looking straight down at the ground, it's only about 3 or 4 feet down. From here to here is only 3 or 4 feet. But if you look at the expanse of the jump, like you look out a little beyond, it's like standing on the edge of the world. Like, this looks way, way the heck down there. And you can see the skier is going to jump, and they're going to take off through the air, and they're going to land somewhere on the downslope. Okay, not where it flattens out, because that'd be kind of crushing. They're going to land somewhere on the downslope. And then something that most people don't realize is that the braking area is actually slanted upward, and that helps, of course, the skiers lose speed, and eventually it flattens out as well. Now, here's what we want to figure out. For starters, we want to figure out the person's maximum velocity when they're using this ski jump. And you can probably realize that the maximum velocity is going to be right smack down there in, we'll call that area B. And when they're at the lowest point in the jump, that's when their velocity is going to be at a maximum. So their velocity in area B, that's when their velocity is going to be at a maximum. And when I look at this problem, okay, and this is one problem where you wouldn't have to generate a diagram, like this diagram would be given to you. When I look at this problem, I see different types of energy. At the start, the person is way high up. Well, they've got gravitational potential energy. Okay? Way down here, they're really low. They're not going to have any gravitational potential energy, but they're really moving, so they've got kinetic energy. So when I look at this diagram, I see different types of energy. I think the law of conservation of energy. Whatever energy you start with, well, that's the energy you're always going to have, just in different forms. Okay, so trying out some new technology here. Whiteboards in stereo. We'll see how this goes. Okay, and I'll tell you what, one thing I'm going to do, I'm dealing with different types of energy, potential energy, kinetic energy. This right here is the lowest point of the jump, so I'm going to say right where area B is, that is where our reference point for potential energy is going to be. That's where our potential energy is going to be 0. Okay, so let's see if we can do this. Well, look up here. They're standing there completely still. Their velocity is equal to 0. They're getting ready to go. What kind of energy do they have? Well, they got no kinetic energy. So right at the top there, their total energy is going to equal to their potential energy. And that's the highest they go. That's the maximum potential energy they're going to have. And of course, when they're down here, and who really cares what happens in between here and here? Okay. When they're way down here, well, look, they're at the 0 point for potential energy. So down there, they don't have any potential energy. So their total energy is going to be their maximum kinetic energy, because that's when they're going the fastest. So their total energy is equal to their maximum potential energy up here, which is going to equal to their maximum kinetic energy down there. Okay, I think we got enough to start figuring this out. Let's see what we can do. What's their maximum potential energy? Okay, okay, so potential energy is going to be mgh. I don't have the mass, but you know what? That'll probably work out in the end. It'll probably cancel out in the end. I'm not too worried about that. Okay. Gravitational field, that's easy, 10 newtons per kilogram. Okay, h. What's our h going to be here? Think about that for a second. All right, remember that this is our 0 point for potential energy. So when we're talking about the height of A here, we're talking about not the height above the parking lot level, not that height. We're talking about this height, the height between A and B. Okay, so there's a potential energy. We can write in the numbers later, mg, ha. What's the maximum kinetic energy going to be? Well, it's going to be half the mass times their velocity, which is Vb, which is the same as their maximum velocity, and that's squared. Oh, nice. M here, so yeah, I don't have to worry about the mass of this thing. The masses cancel out. Substitute in your numbers. G is 10 newtons per kilogram. The height is, remember, the height above the 0 point, so 90 take away 20, the height between A and B, the height above the 0 point, is going to be 70. Okay, don't have to do anything with that. Half, and we're trying to find V max squared. So all we got to do is solve this now. Well, piece of cake to solve it. Take the 2 over the other side, it goes upstairs, and then take the square root of everything over the other side, and you're going to be left with V max is equal to the square root of 2 times 10 times 70, and I believe that works out to 37 meters per second. Done, which is really moving, right? That's like 100 feet per second. Okay, that's A done. We figured out V max. Okay, let's figure out B part now. The elevation of C above the parking lot. Okay, and we should give you actually a little bit more information here. Give me just 1 second while I adjust this ever so slightly. Okay, there we go. I corrected question B there. What we're trying to find now for question B is the elevation of C above the parking lot. If the velocity we want our skiers to have, okay, when they enter this braking area here after they slow up as they go up this hill and then enter the braking area there, we want them to be going 5 meters per second. Okay, I tell you, maybe at the end of all this, I'm going to release a reel of outtakes, but that might have to wait till you're graduated, maybe even till you turn 18, because to be quite frankly, there's probably a lot of swearing on it. So, B part, we want to figure out the elevation of area C above the parking lot. Okay, if the velocity of our skier in C is supposed to be 5 meters per second. Well, again, I look at this and I see different types of energy. Okay, their total energy here, remember, was their potential energy. And that worked out to be what? The mass times the gravitational field times the height of A above the 0 point, which was 70 meters. So that turns out to be 10 times 70, which is 700 times the mass. And again, I have no idea what the mass is, but that's okay. It'll probably cancel out just like it did the last time. So there's their total energy, 700 times whatever their mass is. Okay. Now, up here, their energy was just potential energy. Down here, okay, well, they've got some height above the parking lot, so they have potential energy, and they're also moving, so they have kinetic energy. So when they're in area C, their total energy is going to be the potential energy they have in area C, because they've got some elevation above the reference point, plus their kinetic energy at C. Again, because they're moving there. Now remember, whatever energy you start with, that's the energy you end up with. So their total energy, right here, which we calculated to be 700 times the mass, is going to equal their potential energy at C, which is going to be the mass times the gravitational field times the height of C, plus the kinetic energy at C, which is going to be half the mass times the velocity at C squared. So let's see what we have for an equation now. We got 700m, and over here we have, let's see, the mass times 10 times the height of C, and remember, you want the height of C above the parking lot. Oh, and that's what we're trying to figure out, right? The elevation of C. So, good. In every equation, you need something to solve for. And what do we have over here? Half the mass times the velocity at C squared. And once again, take a look. I got an M term, a mass, everywhere I look, so I can divide both sides by M. Basically, the masses cancel. And what are we left with? Well, we're left with 700 is equal to 10 times hc plus a half times 5 squared. Well, that's a half of 25, which is 12 and a half. So let's figure this out. Okay, take the 12 and a half over to the other side. It's going to become a negative. So you got 700 minus 12 and a half. Take the 10 over to the other side. And it goes down to the bottom. 700 take away 12 and a half. That's 687 and a half. 687 and a half divided by 10 is going to be 68.75 meters. Okay. Is that our answer? Okay. Remember, we want the elevation of C above the parking lot. And this is HC. This is the height of C above our reference point for potential energy. So if we want the height of C above the parking lot, we got to go, for our final answer, the elevation is going to be, well, this distance, HC, 68.75, plus this distance, which is 20 meters, and there is your final answer, 88.75 meters. And that makes sense, because let's face it, it should be lower than the 90 meters. The starting point is above the parking lot, and it is. Now you notice that it's just a tiny little bit lower, and you might scratch your head and say, that can't be right. And you're right, it can't be right, because let's face it, when we were doing this problem, we ignored friction. We also ignored air resistance. If an engineer were doing this problem, they would probably do the problem like we just did, and they'd realize, well, that can't be right. I'm going to have to factor in friction and air resistance, and they probably wouldn't get a truer value for that. But for us, good enough. So again, whenever you look at a problem and you see different types of energy, think law of conservation of energy. The energy you start with is equal to the energy you end with, just in different forms. I will post an assignment on this. Good luck with it. You should have it done for tomorrow, because tomorrow we're going to start taking a look at springs. Bye for now.